Check it.
Okay, welcome back. Today we're going to be talking about operations on imaginary numbers, actually operations on complex numbers, and I'll explain to you the difference as we go along here. So we learned in the previous lesson what an imaginary number is. It's what results when you try to take the square root, or actually any even root of a negative number. So if you have something like this, like the square root of negative 64, you cannot square root a negative number. There's no such thing as the square root of negative 64. Right? If you square a negative 8, you get positive 64. So no such thing as the square root of negative 64. However, what we learned was that you can take a negative square root, you can pull the negative part out, okay, like for instance, we have negative 64 here. You can take the negative part out as a separate multiplier there, and you can call this thing I. And that allows you to do the positive part of the square root, and what you get is 8I. So that's what that is. So that's what we learned last time. This time what we're going to do is take these things and actually add, subtract, multiply, and divide them. So here, the first example we have here, we're multiplying two imaginary numbers. But here's the thing. While they're like this, while there are negative square roots here, square roots of negative numbers, you cannot touch these.
I told you, homeboy, you can't touch this.
Like, you cannot even do anything with them while they are negative square roots. What you need to do is change them into imaginary numbers first before you can touch them. So, can you multiply these? No. You need to go ahead and take the negative part out like I did here. This became 8I. And what does this become here? Well, this is going to be negative 81, where you're going to make this a positive 81 with times a negative 1 like that, right? This becomes your I, and what you get here is 9I. So basically you're just doing the square root and you're slapping an I on the end. But once you do that, you now have an imaginary number times another imaginary number, and you may, or you can actually multiply these. You cannot. It's impossible to multiply them while they're in this form. You might think, well, what if I just multiply the two negatives? It'll cancel out and you'll have a positive. Nope, that's not the way it works. It's completely wrong. So anyway, you change these two imaginary numbers, you multiply them now, and you treat them just like you would treat x. So if this was 8x times 9x, it'd be 72x. Well, this is, 72x squared, right? Because there's two x's. Well, in this case, there's two i's. So 72i squared. And what we learned in yesterday's lesson is that I squared is negative 1. So this is actually 72 times negative 1, which means this is negative 72. However, this is not what we want for this problem. If you notice up here, it says, give your answer in a plus bi form. What is a plus bi form? We talked about this briefly in the lesson yesterday. If you have a real number, like 3, and you add it to an imaginary number, like 8i, when you put in a real number with an imaginary number like this, when you add them or subtract them, this is called a complex number. And a complex number should be written in the form a plus bi, which is the form that we have here. So what's going on with this thing here? There's an a, but there's no bi. Why? Because the imaginary stuff all canceled out when we got the I squared. So how do we write this in a plus bi form if there's no bi? Well, it's pretty simple actually. You write the a, which is negative 72, and then you put a plus 0i. Now it's in a plus bi form. So the real part of this, the a is negative 72, and the b is 0. That's the imaginary part. So this is not what you're boxing. This is what you're boxing. Let's try the next example. Now we're adding. There's a plus in between here. We're going to add these two. So we have 2 times, we already know this is 9i from the last couple of problems, and then it's 3 plus times rather. Well, what's that going to be? Take a wild guess. Well, take the square root of 9, it's 3, and then this is going to create an I. So even without breaking it down to positive 9 and negative 1, you can see this is going to be 3i, right? So there you go. And now simplify. This is going to be 18i right here, right? 2 times 9i is 18i. Plus, and this is going to be 9i right here. 3 times 3, right? 3 times 3 is 9i. So you're adding, what do you get? Well, 18 plus 9 is 27. And I, they're both I, so it's 27i. Not I squared, you're not multiplying. So you have that. Now, you're supposed to be writing this in a plus bi form. So where's your a, what's your bi? Remember, a plus bi. Well, this is a 27i, so it goes actually under the bi. This is over here, like that. So what's missing is the a, so we'll put a 0 in for a. And there's your a plus bi answer. Okay, this next one is the square root of negative 128. And right away, you know you can't do anything with it because there's a negative in here. So the first thing you want to do is take the positive and get rid of the negative by sticking it outside in its own radical. That's going to become an I, right? So right away, and you can't put the I after the radical, so you put it in front of the radical like this, and you get that. Now the question is, what do we do with the square root of 128? It's not a perfect square. So what we do is we make our factor tree. What are two numbers that multiply to give me 128? Well, 64 times 2 might work. Now, you might want to stop right now and just take the square root right away, but since we're doing factor trees here, let's go all the way down. So another way to break down 64 is 16 times 4, and that's already a prime number 2. This can become 4 times 4. That can be 2 times 2. That's a 2. And finally, we get 2 times 2 times 2 times 2 times 2 times 2 times 2. So 128 is actually 2 to the 7th power. How many perfect squares do we have in here? Well, there's a perfect square there, there, and there. That's 2 squared, 2 squared, and 2 squared. And then we have one lonely 2 here that's not squared. So when we go to do the square root here, this is going to be the square root of 2 squared, 2 squared, 2 squared, and then just plain old 2. All of the squares cancel out the square roots, and we get 2 times 2 times 2 is 8i radical 2. But here's the problem. This is not a plus bi form because this has an I in it. So this is your bi. Where's your a? You don't have it. So 0 plus 8i radical 2 is your a plus bi answer right there. Okay, for this one we have multiplication. We have things that we cannot touch because they're negative square roots, so we won't touch those. We will change them into imaginary numbers just like we did way up here, right? But what's different here is that these aren't perfect squares this time, so we have to do a factor tree for each one of these. So first we need to do 27, and then we need to do 48. So 27, 9 times 3, which is 3 times 3 times 3. And you can see there's a perfect square right here, 3 squared, and there's a leftover 3 there. For 48, well, let's see, 16 times 3, and that would be 8 times 2 times 3, right? And the 8 becomes 4 times 2, and oops, that's supposed to be a 3 on the end there. And then finally the 4 becomes 2 times 2, so this right here, 2 times 2, and this is already a 2, and this is already a 2, and this is already a 3. Now please draw your entire factor tree. I saw some people in the homework doing something like they wouldn't draw the entire thing because they thought they didn't have to. No. Keep bringing down, okay, your numbers that are prime. So anyway, we get all this here. So we have perfect square there, and we have a 3 there. So how do we square root 27? Well, negative 27 actually. Well, this becomes 3 squared times 3 times negative 1. That's all going to be right there. And for the 48, that's going to be times now. For the 48, we have 2 squared, another 2 squared, and a 3. And for the negative, we have a negative 1. So what happens here? Those cancel out, those cancel out, those cancel out. So this becomes 3 root 3, 3 radical 3. And now there's an I right there. You're not supposed to put the I after the radical. You put it in front of the radical. So you put the I right here. Now we have times right there. This is going to be 2 times 2, which is 4. There's your I. Let's just go ahead and do that right now. And then you have your radical 3. So we need to multiply these now. Well, multiply the outside stuff first, and then multiply the stuff inside the radical second. What is 3i times 4i? Well, it's 3 times 4 is 12, and I times I is I squared. So that's 12i squared. And what's radical 3 times radical 3? Well, that becomes radical 9, because you can multiply radicals just like you can multiply regular numbers. And radical 9, we all know, is 3. So now you have 12 times 3, which is 36, I squared. And wait, I squared equals negative 1. So this is now 36 times negative 1, which is negative 36. Okay, but wait, it has to be a plus bi form, so we need to add a plus 0i. And finally, we're there. So you can see this problem took a little bit more work than the one up here, which looks like almost exactly the same thing because, well, you needed to make factor trees and stuff. All right, so that's basic adding and multiplying. How about FOIL? Yeah, you can multiply a binomial times a binomial where the binomials are imaginary. You can do that. So once again, if you have a negative inside of a square root, don't even think about starting to multiply right away because as MC Hammer once said,
I told you, homeboy, you can't touch this.
However, if you do want to touch these things, you have to turn them into imaginary numbers. So what are these going to be as imaginary numbers? Well, at this point, I hope that you can pretty much do this in your head. Square root of 36 is 6, and that's going to give you an I. So this is going to be 6I. And then for this is going to be 9I. We already did that one several times. Now that you've written them as imaginary numbers, you can go ahead and FOIL now. So let's go ahead and do that. Let's distribute the 5, and we get 5 times 4 is 20. And 5 times 9I is 45I. We'll distribute the 6I here. We get 24I right there. And 54, 6 times 9 is 54. I times I is I squared. Now your answer has to be an A plus BI. Is it? No, it's not. So let's keep simplifying now. Well, one thing we can definitely do is combine like terms in the middle here, right? These two add together. And that's going to be 69I right there. 45 plus 24 is 69. And they're both I. You're adding, so you're not going to have an I squared. This right here is going to be an this is an I squared. This is going to become a -1. So you're going to multiply 54 by -1. So actually this is negative 54 right here. So 20 minus 54 is negative 34, right? 20 minus 54. Well, is this an A plus BI form? Well, it's backwards. Actually, it's BI plus A. So you want to switch this around. Now it's correct. Okay, this next one is adding. Now, don't be fooled by the parentheses. People see parentheses and think, oh, I'm multiplying. Nope. You see that right there? That's called a plus sign. When there's a plus sign, you add. Now, how do you add two complex numbers? Well, here's the thing. The real numbers, the A part and A plus BI, they're both A plus BI. You notice that? The real part is the A's, and they're like terms. The imaginary part are the BI's. They're like terms, and that's it. So basically just combining like terms. So all you can add here are the -3 and the +4. -3 plus 4 is 1. And then you have 5i plus -2i, or the same as 5i minus 2i, which is 3i. And that's it. Okay, now we're subtracting. We have a binomial minus a binomial. Okay, it's just like adding up here. It's like terms. However, what's different about subtracting is whenever you have a minus in front of a set of parentheses, you have to regard it as a -1 and distribute that negative to both of the things in the parentheses here. So what happens? Now you have 5 plus I. When you distribute this negative, -1 times -4 is now +4, and -1 times 7i is -7i. And now that you've done that, you just combine like terms, but you need to distribute the negative. So if you're subtracting, distribute the negative to the second set of parentheses. Now, where are like terms here? We have 5 and +4, which is 9. We have I minus 7i is -6i, and now we're done. Okay, we did adding, we did subtracting, we did multiplying. Now it's time for dividing. And dividing is going to be the most complicated one. There's several types of dividing, so let's go through them all. There's really simple dividing, where you take a simple imaginary number and divide it. Well, I mean, if this was 6x over 3, right, 6x over 3, you'd realize that 6 over 3 was 2, and that you're going to get 2x. Or if you want to think of it as reducing a fraction, it's 2x over 1, which is still 2x. Well, there's no difference when you're working with I. You treat I like you treat x. So the algebraic skills are identical. This is going to be 2i. The problem is it's not an A plus BI form, right? Yes, this becomes a 2 right here, but where's your A plus BI form? Well, this is obviously your BI, so what you need is the A is missing. You need an A placeholder, so put a 0 there, and there you go. Now, this was one term in the numerator, one term in the denominator. Very simple. This is 2 terms in the numerator, 2 on top, 1 on the bottom. When you have 2 terms in the top of a fraction and only 1 term on the bottom, you do something called splitting the fraction, where you divide this divided by this, plus, in this case the sign is plus, this divided by this. Okay? And if you draw it correctly, it kind of looks like a heart. So I call it the heart method. Okay, the heart method, aka splitting the fraction, is what you do when you have multiple things on the top of a fraction but only one thing in the denominator. So if, let's say, you had 8 plus 7x plus 3x squared over 3, well, then it wouldn't be a heart anymore, it'd be like a flower, but you would divide all of them by the denominator, right? So what do we have here? We have 8 over 3 plus 10 over 3. And since we want A plus BI, we want to separate the B from the I, so that's what I'm doing here. And there you go, you're done. Splitting the fraction using the heart method. How romantic. Okay, we're going to move on to the next thing here. Now, this is part of dividing, so this is a little review well, it's actually, maybe it's not a review, maybe it's an introduction to something, but it's called Rationalizing the Denominator. When you have a fraction, there are several things that cannot go into a denominator of a fraction. One of them is an irrational number. You should never have an irrational number in the bottom of your fraction. And I mentioned in the lessons that an irrational number is when you take the square root of a number and it comes out to be a decimal. Like square root of 2 is irrational, because if you try to square root it, you'll get a decimal. And the decimals that come from doing square roots are always, always, always irrational. So if you do the square root of 25, for instance, you get a whole number, that's rational. But if you do the square root of 26, you're going to get 5 point something, and it'll be one of these crazy decimals that goes on forever, never repeats, just like pi 3.141592. It just goes on forever and ever, right? So we don't want to have a denominator like that. So how do we rationalize, meaning make rational, this irrational denominator? Well, here's what we do. We use a trick. We realize that this is the square root of 2. And if you want to make the square root of 2 into a whole number, you can square it. If you square the square root, then the square root becomes a whole number. But here's the thing, you can't just square the fraction. It will change the value of it. Like if you took this whole fraction and squared it, it wouldn't be the same value anymore. But what you can do is multiply it by something that won't change the value. So what can you multiply by? Well, if I want to change this into a whole number, I need to square it by multiplying it times itself. That's going to become a 2. See, square root of 2 times square root of 2 is the square root of 2 squared, which is 2. However, to keep it balanced, I'm going to do the same thing on the top. Now, what's the value of this fraction here? It is equal to 1, because it's something over itself. Multiplying this by a 1 does not change its value, so this is legal. Okay, you just have to make sure whatever you do to the bottom, you do to the top. Like with an equation, whatever you do to the right, you do to the left. Whatever, on a fraction, you have to do the same thing to the bottom as the top. So the bottom we're multiplying by the square root of 2. We better do the same thing to the top, and we get 3 radical 2 on top. And there you go. The denominator is now a rational number. The numerator is not anymore, but that doesn't matter. It's okay to have an irrational numerator. You just can't have an irrational denominator. Now, rationalize the denominator of this. 3 over 2i. I don't know why I'm still using the red marker. Let me change back to blue here. Okay, so how do we make this rational? Now, why is this irrational? Well, it's imaginary. Rational numbers are real numbers. So the fact that this is imaginary, it's not real, means it's also not rational. Okay, so imaginary numbers are irrational as well as square roots of anything that isn't a perfect square. So how do we get rid of this? Well, we're going to use the same trick basically. If you know that you have a single imaginary number in your denominator, what you can do is use the fact that I times I equals I squared, and I squared is -1. So if you can just multiply this bottom by another I, the bottom becomes 2i squared, which is 2 times -1, which is -2. Hey, no more imaginary number in the denominator. But of course, if you want to balance this out, you better do it to the top as well. So the top becomes 3i, okay? And when you finish simplifying, you get -3 over 2i. And there you go. But wait, oh, that's not a plus bi form. You want to make that a plus bi, you need to put a 0 minus. Okay, there you go. Now it's a plus bi, where b is -3 over 2. So that's how you rationalize a denominator when there's a single term in the denominator. If it's a square root, just multiply by the same square root. If it's an imaginary number, multiply by I, top and bottom. All right, let's try that out here. We're going to divide this, which is also rationalizing it. Here we go. Heart method. Okay, how romantic. There we go. Just in time for Valentine's Day. Not, it's November. Okay, so we're going to write 8 over 2i. Whatever the sign is, if this was a minus, I put a minus here. This is a plus, I'll put a plus here. And then we have 10i over 2i. 10i over 2i. So that's the first step. Now, what can we simplify here? Well, one thing we can simplify is that this becomes 4 over 1 if you reduce it, right? So this 8 over 2, you can divide the top by 2, right? And the bottom by 2, and this becomes 4, and this is a 1. So you get 4 over I, like that. Now here, you can divide this by 2 and this by, divide this by 2 and get a 5, and this by 2 and get a 1. And what else can you do? Well, you have I over I here, and these cancel out because they become a 1, right? Anything over itself is 1. So this just becomes a plain old 5, okay? So are you at a plus bi form? Well, it's backwards. So if you flip it around, you have 5 plus 4 over I, but that's not a plus bi. That's more like a plus b over I, like that. And that's no good. You cannot have an I in a denominator. So that means this needs to be rationalized. So what do? When you see that, remember, your goal is to get to a plus bi, like that, not that, no good. So we need to do that trick where we multiply the top and bottom by I. That's what we're going to do now. We're going to multiply the top of this by I. Let's do this in red so it stands out. And the bottom by I. Now this becomes 5 plus 4i on top and I squared on the bottom. Well, what's good about that? I squared is actually -1. So this is 5 plus 4i over -1. Anytime you divide by -1, all you're doing is changing the sign. So this becomes 5 minus 4i. And there you go. Okay, we're going to divide. Now you notice that all the division questions we did so far were a single number in the denominator, right? 6 over 3. This thing over 3, right? This over radical 2. This over 2i. Single terms. One term, one term, one term. Now we have two terms. Two terms. Well, in order to get rid of a two-term denominator, where one of them, one of the terms is something I, you have to use something called a conjugate. Now we talked about conjugates when we did factoring. Okay, like if we had a difference of squares, like I don't know, x squared minus 4. That's the difference of squares. You get x plus 4, x minus 4. These were called conjugates. And conjugates were when you had a binomial and a binomial that were exactly the same. The only difference was one had a plus in the middle and one had a minus in the middle. Well, complex conjugates are the exact same idea, except there's an I in the mix here. So here's what you're going to do. If you have an a plus bi in your denominator, like we do here, or like we do here, here's what you're going to do. You're going to realize that, hopefully, that if you multiply an a plus bi times its conjugate, the imaginary parts disappear. And I'll show you how that works right now. So what we're going to do here is multiply by the conjugate. Now, what's the conjugate of 3 plus I? It's 3 minus I. We're going to multiply these, FOIL. And when we do that, we're going to get a difference of squares, which is going to be real. You'll see this in a moment. Now, to keep it balanced, we have to do the same thing to the top. Why? Because that makes this whole fraction worth 1. And multiplying the original problem times 1 does not change its value. So we get here. So far, you see this problem. You see that there's two terms down here. You can't just use one of the tricks that we did in the last couple of problems. You realize, oh, I need a conjugate. The conjugate of 3 plus I is 3 minus I. So go ahead and now we'll multiply the top here. We get 15 minus 5i. That's the top. The bottom is a binomial times a binomial. Two things times two things. We're going to have to FOIL that. So I'll do this over on the scrap area on the side here. By the way, don't put your scrap work with your steps. When you're being graded, keep your steps nice and clean. Do your scrap work off on the side here. So I'll just do the 3 plus I times 3 minus I here. 3 times 3 is 9. 3 times negative I is negative 3i. I times 3 is positive 3i. And I times negative I is negative I squared. You'll notice that just like with other conjugates, the two middle terms will cancel out. That's the beauty of conjugates. So this becomes 9 minus I squared. Now what is I squared? It's -1. So this actually becomes 9 minus -1. Minus negative is the same as saying plus. So this is actually 10. So that becomes a 10. So there you go. No more imaginary numbers by using a conjugate. It's like magic. However, we do have to keep going now because we have a fraction, but now we can use the heart method because there's two things on the top and only one thing on the bottom. Okay, kind of a squiggly looking heart, but there it goes. So now we have 15 over 10 minus this time 5 over 10 I. And these can both be reduced since they're all multiples of 5. Divide the top and bottom by 5, you get 3 over 2. Divide the top and bottom by 5, you get 1 over 2 I. Is this an a plus bi form? Yes, it is. All right, so we have 2 plus 4i on the top. But the important thing is that the bottom becomes rationalized here. And the only way to get rid of the imaginary stuff in the denominator when you have two terms is to use the conjugate. So what's the conjugate of 5 plus 2i? It's 5 minus 2i. And if you use that on the bottom, you also have to use it on the top for balance. Keep the equation, well, it's not an equation, keep the fraction balanced here. So let's FOIL all of this. Okay, this time I'll do the bottom first. So the bottom, we'll do it over here, 5 plus 2i times 5 minus 2i. 5 times 5 is 25. 5 times negative 2i is negative 10i. 2 times 2i times 5 is positive 10i. Right away, oops, I wrote x. Right away, you see that these are going to cancel out, which is why we use conjugates. And then 2i times negative 2i is negative 4i squared. So this becomes 25. And then this is negative 4i times negative 1. You see the I squared there? That's a negative 1. So actually, that becomes positive 4. So this is 25 plus 4, which is 29. So the bottom here is 29. Okay, no more imaginary numbers. Perfect. Now, we also have to FOIL the top here. So 2 plus 4i times 5 minus 2i. 2 times. Now, this is not going to be just a regular number here because these are not conjugates. 2 times 5 is 10. 2 times negative 2i is negative 4i. 4i times 5 is 20i. And 4i, this is going to be negative 8i squared. So let's see what we can do. We can combine these two here. This becomes 16i. This is going to become negative 8 times negative 1, which is positive 8. And that's a 10 right there. You can add the 10 and the 8 together. You get 18 plus 16i. And that's what's going to go over here. 18 plus 16i. Now, we're not done because this is not a plus bi form until we split it. So go ahead and split the fraction. Okay? And we get 18 over 29. There's a plus here. 16 over 29i. Not the prettiest thing in the world, but it is correct. Okay, the last example is to show you what to do if you're solving an equation and you end up with a negative on one side of the equal sign. So let's solve this equation right here. Now, this doesn't have an x in it. It only has an x squared. So you don't need the quadratic formula, and there's no factoring to be done here. All you need to do is solve it algebra 1 style, basically. So get the x by itself. So we'll start off by subtracting 125 from both sides. Okay, this wouldn't work if there was a x squared and a regular x, but there's no regular x, it's just a squared, so we can do this. We get here, we're going to divide both sides by 5, and now this becomes x squared equals, and this is going to be negative 25, like that. And then you say, all right, what do I do now? Well, you need to square root, to get rid of the square here, you need to square root both sides, like that. So now the square root knocks off the square here, but what do you get? You don't get an x. Remember, with variables, you need to have an absolute value here. Now, what is this? Well, this is 5i, right? So you get that. Now, when you drop the absolute value bars, that creates a plus and minus 5i. So there's actually two answers here when you drop the bars. Now, is this a plus bi form? Well, not quite unless you add a 0 here. So you have two answers, 0 plus 5i and 0 minus 5i. And that's what this is right here. Okay, that's everything. See you at the next video.
Check this.